Okay, so welcome everybody. Today I'm very happy to welcome Greene from the University of Princeton. She's extremely distinguished lecturer, and she spent this week with us, but unfortunately she's busy and she must go back to Princeton this afternoon. I think her visitor schedule is fairly full, but if you're lucky and find this spot, then you might know. You can send her an email. So,
come to Princeton.
Or come to Princeton, even better. So, Jenny completed her undergraduate studies at Yale. After that, she went to Harvard. She came to Harvard here, where she obtained her PhD degree. The thesis was about black holes, and the title was the growth of black holes from primordial seeds to local demographics. And since then, Jenny has become a well-known expert of black hole studies. So after obtaining her degree, Jenny was a postdoctoral fellow at Carnegie Princeton. Then she became professor at UT Austin, and shortly after she moved to her current position, and she's a professor at Princeton. So as I mentioned, Jenny is an expert in all kinds of black hole studies involving supermassive black holes. She is interested in black hole demographics, especially a particular focus on black holes in both galaxies. She also studies black hole binaries. I think we will also hear a little bit about black hole binaries today. And of course, she's very keen to learn about the seeds of supermassive black holes. So the title, she changed her.
Sorry.
She changed her
I always do that. I didn't remember what the
her original title was Black Holes, not in the intermediate, but there's a new title which she can tell you. So, Jenny,
all right. Thank you. Well, first of all, I want to say I'm really honored to be a Steve Murray lecturer, and he was a great presence here the entire time that I was here in graduate school, and it's quite an honor. So my new title, Mergers, Active Galaxies, and the Gravitational Wave Background. Yesterday, Anil and I talked about black holes and dwarf galaxies and what it might teach us about the seeds of supermassive black holes. So I thought today I should focus on, now we know we can make them, what can we learn about the coevolution of galaxies and black holes? And I like to think about this as a life cycle, but many of you have known me for a while. Now I have a 2-year-old. So in terms of life cycle, it's very interesting to come back to your place of graduate study. And now my mind just keys into all the playgrounds instead of the bars. It's just, so anyway, life cycles. So we know we live in a hierarchical universe. Actually, one more thing. I just want to say that a lot of this work has been led by Andy Goulding, who is my phenomenal postdoc. Many of you also know him since he was a postdoc here before, but I also want to acknowledge Chris Pardo. He's just gone on to a postdoc at Caltech, and Chiara Mingarelli, who's at CCA. So we know galaxy mergers happen, and we know that there are black holes in all massive galaxies, but then there are a whole bunch of questions about how the interaction between the galaxies, the black holes, and the mergers may impact both the growth of the black hole and the evolution of the galaxy, and that's what I want to talk about today. So first of all, I want to take a limited stab at this age-old question of whether galaxy mergers are needed to trigger AGN activity. I also then want to think about the very pressing and timely question of whether once we have pairs of black holes come together in galaxy mergers, they ever actually merge and make gravitational waves that we might someday detect. And finally, the question of how you shut off star formation in galaxies. You know, when I got here as a graduate student, the M-sigma relation was just happening, and people were really excited, including Lars and his group, about the idea that energy from the radiating black hole could be responsible for shutting off, expelling gas in the galaxy, shutting off star formation, and making old, red, and dead galaxies. So in the last part of my talk, I'm going to come back to this question of what shuts off star formation in big galaxies. So we're going to start with this question of whether mergers are important in the fueling of AGN. You've probably heard many, many talks about this question. You can read many, many papers. And it's clear that the fueling mechanism of supermassive black holes is likely to be a function of their luminosity. And so at low luminosity, where most of local active galaxies reside, it has been shown, I think, pretty definitively that lots of secular processes in the galaxy can provide enough bits of dribbles of gas to fuel a bit of AGN activity. So that could be bars, that could be minor mergers, that could be a GMC wanders too close, maybe there's a gas cloud in the galactic center, maybe not, maybe it's a star. Anyway, so at low luminosities where you don't need too much gas, lots of processes can trigger AGN fueling, but it has remained actually quite contentious as you get to very high luminosities, whether the only way that you can get this solar mass a year to dissipate 7 orders of magnitude in angular momentum and finally accrete onto the black hole, whether that requires mergers. And that sort of has been the long-standing theoretical argument, that it really has to be mergers at high luminosity because we can't think of any other way to do it. If you go to AGN conferences, you can find polite but very heated discussions about this question based on data. And so Carolyn Vilforth has done a really careful job of looking at quasars in HST fields and looking for signs of mergers. And she claims there's no difference in a mass-matched sample of inactive galaxies and active galaxies. And so therefore, mergers cannot be the only way to fuel relatively luminous AGN. Elad Glickman has taken a different approach. She finds these red quasars that look to be the most luminous quasars at all redshifts, and nearly all of them are in mergers. Of course, she's selecting things to be red. That means dusty. Maybe she's biased towards mergers. And this is a super hard problem because luminous quasars, it's really hard to figure out what their host galaxies are doing. So as a spoiler alert, I am not going to answer this question completely, but we wanted to try to answer a more limited question, which is just as a function of luminosity, can we argue that mergers at least play an important role in triggering AGN fueling? And we wanted to go back to this question because we had some new exciting data. So we have this Hyper Supreme Camera survey that we're doing in collaboration with the Japanese, which gives us a very large sample of both active accreting black holes and the ability to find mergers out to redshift 1 with pretty high fidelity. So just briefly about HSC, you always have to compare your survey to the full moon. So HSC is quite deep and also very high angular resolution for a ground-based imaging survey. So we have a median seeing of 0.5 to 0.7 arc seconds. And this was the SuprimeCam field of view. This was state-of-the-art with Subaru, which is a wide field of view. And this is the 1.8 square degree field of view of HSC. Okay, so we are doing a spectacular imaging survey. We're about halfway through now, finally. It has 3 layers. 1,400 square degree wide layer to I of 26, 30 square degree deep layer to 27, and then this ultra deep layer in Cosmos, 2 HSC pointings. So most of what I'll be talking about was coming from the wide layer, which is plenty deep. In fact, one of our favorite games in the HSC collaboration is to compare HSC and Sloan images. It's mind-blowing. Okay, so how do we find the AGN? We just used WISE colors. So in this work, Andy just did a standard color selection. So basically, the AGN have these dust power laws that are rising, hot dust, separate pretty cleanly from galaxies for very luminous quasars. And when we fold in the I-band data from HSC, we can even separate things into obscured and unobscured. It's a lot easier to see mergers in unobscured things where we don't have to contend with the light from the quasar. And so we had a sample of 3,000 AGN. We think we can do okay, and morphologies for redshifts less than 1. So I'm not going to get into the details of how Andy built his merger sample, but our idea was instead of starting with the AGN and asking what fraction are in mergers, we want to look at all the mergers and ask what fraction are luminous AGN, and that should be a much higher signal-to-noise measurement and much less sensitive to the fact that the AGN timescale is shorter than the merger timescale. And so what we basically did was Andy measured a whole bunch of parametric and non-parametric measurements from the HSC images, including things that you all have heard about. How asymmetric are they? What are these Gini coefficients? He also did Sersic fits. And we also then did a huge effort with all of the summer undergraduates a couple of years ago to visually classify a large sample. And then he fed all of these things into a decision tree random forest. Half of the visual classifications were used for training, and then half were used to build these probability distributions. So these are the classifications by eye, and these are the probabilities that come from the random forest. And so Andy just made cuts in these probability distributions for the entire sample and was able to therefore select these totally gorgeous merger galaxies. Okay. Often people get confused and think these must be HST images because they're so pretty, but no, these are the HSC images. Okay, so here's the result as a function of stellar mass now in 3 redshift bins. This is the fraction of galaxies that are actively accreting as probed by the WISE colors for the mergers in red, the major mergers in purple, that's a detail, and then the non-interacting galaxies in orange. And so what you can very clearly see, right, so that's the non-interacting AGN fraction down around 1%, and there is a substantial boost in the AGN fraction between the non-interacting and the merger galaxies. So that is to say, it is clear that mergers do trigger AGN activity. We've seen this before at lower luminosity, at low redshift. For instance, Sarah Ellison with pair counts clearly showed that as pairs get closer together, the AGN fraction goes up. So this is a comparable result, but for a much more luminous sample. We can even sort of see that luminosity effects within our own data. So we just removed the top 25% most luminous AGN, which are shown in hashed here, and the AGN fractions drop dramatically when you remove those most luminous things, whereas they don't drop in the non-interacting sample. And so there is even a trend that as you go to the most luminous things, the AGN fraction, the triggering goes up even more. Okay. So like I told you, I cannot fully answer the question that I want to answer, which is, are mergers required to trigger these luminous quasars? But I can say that the AGN fraction goes up by something like a factor of 6 to even 10 for the most luminous things that we see at redshift 1. So it's clear that mergers play an important role. Our next step really is to work with simulations and try to calibrate how often we think we would see the AGN on during the course of the merger and ask if this AGN fraction indeed corresponds to something like 100% of AGNs being triggered in mergers. And this has to do with our incompleteness in terms of our merger samples and all of that. So that's the basic punchline. Mergers do boost AGN fractions by a large amount at these high luminosities, and more work is required to address the question whether at the highest luminosities mergers are really needed to fuel AGN. Okay. So we have these galaxies. They have massive black holes in them. They merge. The black holes are massive and dense. They should sink to the centers of their galaxies by dynamical friction. They should form bound pairs of black holes, and potentially, we hope, would merge and also emit gravitational waves. A large embarrassment for the field is that neither observationally nor theoretically, I think, have we completely converged on whether or not black holes actually do succeed in merging at the centers of galaxies. We do not know, and it is very hard to predict, what we expect the gravitational wave background to be. But people are going to measure it soon, I hope, and at the very, very most massive black holes, so 10 to the 8, 10 to the 9 solar mass black holes, pulsar timing arrays are going to be the way to detect the persistent gravitational wave background. And so you have these millisecond pulsars that are exquisite clocks, and you can measure tiny differences in arrival times from the pulsars, which is you would get correlated changes as the gravitational waves pass through the galaxy. And so that is what the PTAs are doing. Of course, they are only sensitive to very, very low frequencies coming from these mergers of very, very massive black holes. So yesterday I talked about how excited we are about space-based gravitational wave experiments that should see the mergers of 10 to the 4 solar mass black holes at redshift 10. They can hopefully tell us about seeds. But today I want to talk a little bit about what we hope will be an imminent detection of the gravitational wave background from PTAs. And so when we think about this background, the black holes do not merge in the PTA band. So what we're seeing is the integrated gravitational wave background from an in-spiral phase for all of the black holes out to some redshift that isn't totally known. So the superposition of gravitational waves. It's dominated by black holes that are more massive than 10 to the 8, just because of the frequency range, and probably redshifts less than 1. Kelly here, when he was working with Lars, suggested that most of those mergers are happening closer to a redshift of 0.3, so it's still uncertain exactly when the mergers happen. Of course, it's uncertain whether the mergers happen. One of the big uncertainties is we need to know the black hole mass distribution very well at the high mass end, because the strain is very sensitive to the black hole mass that you assume. Usually the way this game is played in terms of making predictions of the background is to take galaxy properties, whether velocity dispersion distributions or luminosity functions, and translate those into black hole masses. But of course, our knowledge of how to translate from, say, a bulge luminosity to a black hole mass at very high black hole mass is pretty uncertain. As you saw with M87, we're still working out the systematics of the black hole mass measurements, and also most of the objects that have been targeted so far live in the centers of clusters, so we don't understand the scatter here at all. Furthermore, there's a long-standing problem, so we think we understand that the black holes will sink under dynamical friction till they get to parsec kinds of scales. They become a hard binary. They continue to lose angular momentum by interaction scatterings of stars. And then you get to this point where you run out of stars, this so-called final parsec problem. And you may well be able to circumvent it through gas disks. You may well be able to circumvent it through triaxial potentials, which will continue to fill the loss cone and provide you more stars. The timescales of this are uncertain, and whether it happens are uncertain. The spatial scales are prohibitive, so we can't just take pictures and find subparsec binaries. And if you stall here, then you're nowhere near close enough for gravitational waves to bring you together. And so unlike LIGO, where we've been pleasantly surprised by how massive black hole pairs can be and how loud the gravitational wave universe is, it's quite possible that we will be very disappointed if indeed many black holes stall. So here was Luke Kelly's work, just showing as a function of binary separation what typically is the dominant mechanism. And so you can see here where this final parsec problem may plague us, that it could be viscous drag is the gas disks helping dissipate angular momentum, and it's not till down here that the gravitational waves completely dominate the in-spiral. So you can almost put on one slide all of the possible black hole binaries that people have talked about at these sort of sub-parsec scales. This one, I think, is fairly uncontroversial. At 7 parsecs, 2 radio cores really seems to be a pair of black holes. There's been lots of discussion of whether you could get quasi-periodic variability from the secondary kicking the accretion disk. And so it seems like most of these targets are unlikely to be real binaries, but that's still in play. Then lots of work looking for strange velocity profiles in broad emission lines. We did a bunch of work looking for velocity offsets, so go back to the same quasar again and see if you see radial velocity shifts, which you should see if there are binaries. We don't find anything. And I learned today that there may be a black hole binary that is one black hole lensing the accretion disk of the other black hole, so you should talk to Dan about that possibility. But, you know, again, embarrassingly, we really have not made a lot of observational progress. So we did something completely serendipitously that does not get us to sub-parsec scales, but is kind of fun to think about in terms of how to predict the gravitational wave background. And we came to this source for completely different reasons. So this is one of the most luminous accreting black holes within a redshift of 0.2. So it's this guy here. It's, you know, it's not as luminous as the most luminous quasars in the universe, but as far as objects where you can spatially resolve what the gas is doing, this is one of the most luminous around. And so my former thesis student, Ailey Sun, was really interested because this thing is surrounded by a big O3 nebula. We thought maybe there was a bunch of feedback going on. So we got HST and Chandra time actually to study this O3, which is this green stuff out here. And Andy was looking at the data because we'd finally convinced an undergraduate to do this project with us. And lo and behold, there were 2 little cores. So that's kind of fun. The separation, again, this is not a sub-parsec binary. We couldn't possibly resolve that with HST. But this is 400 parsecs, and it is very, very luminous. Not only do we see 2 cores in the narrowband O3 image, we also see 2 clear cores in the stellar light, and they lie right on top of each other. So Andy spent a lot of time trying to model this as one galaxy with a dust disk in between, and did not think he could get a good fit to the photometry that way. So we tried to argue that this is indeed 2 accreting black holes, both so luminous that if they were both at Eddington, they would be each 5 times 10 to the 8 or 4 times 10 to the 8. Now, of course, people have been studying pairs of AGN for a long time, and Chandra has been quite a leader in this field, NGC 6240 being one famous example, but all of these double-peaked O3 things, the gold standard has always been to follow them up in the X-ray, so this is not news to this audience, I'm sure. And of course, you would like to know if I can prove to you that there are really 2 accreting black holes in this source. We got X-ray data, so maybe we can do a little bit better. Turns out that this guy, which is very luminous in Ys and very luminous in its O3, well, it's kind of pathetic in the X-ray. We'd expect 10 to the 45 based on the Ys luminosity, but there are basically no hard photons, and it seems to be extremely Compton thick, like above 10 to the 25. And so this seems to be a situation where we really need a next-generation X-ray telescope, but certainly sources like this are not going to be prodigious X-ray emitting things. There is a radio detection, but at too large spatial resolution to say. So this is high on our priority list, is to get higher spatial resolution radio and see if we can detect 2 cores there. For the time being, while it is not a slam dunk, I think it is quite likely that the fact that we see both the line emission and the stellar cores suggests that we do have a pair of black holes and that they are both very massive. So, if these things can merge seamlessly, then they would be merging just about today. We see the thing at redshift 0.2, and we're right about here, so we're at the end of the dynamical friction phase and about to enter the stellar hardening phase. And the agglomeration of all of this time, if we do not get hung up at the last parsec, basically means that this pair of black holes would be merging today. And so that just led us to think, well, can we actually put some interesting or any bounds on the expected gravitational wave background based on the fact that this object exists? So let's just assume that these black holes are going to merge and ask what we expect from the gravitational wave background, okay? So we can make very, very pessimistic assumptions that this is the only such object in the universe, and so that its number density is constant with redshift, and that that mass is the only mass that's merging, and that will give us a very pessimistic number. But of course, we can do better than that because we have AGN luminosity functions. And so what we did to sort of bracket the possible range of gravitational wave backgrounds, again, motivated by this source, is we said, okay, what is the number of objects that live in this same very, very luminous in WISE, very luminous in O3 region at redshift 0.2, and let's just assume that some small fraction of them are pairs. And then we can just scale the quasar luminosity function with time and just assume that number density scaled by the luminosity function. And we can assume we know the black hole mass function and that only basically one-to-one mergers are going to contribute to the background. This is our very, very pessimistic characteristic strain if we just have this one source. And this is our best guess if we assume some small fraction of all of the quasars are in this merging phase and then extrapolate with the luminosity function. So here's where nanograv upper limits are today. And this is already eating into some very optimistic predictions for the gravitational wave background because, as I said, we don't know the black hole mass function and we don't know the merger rate and we don't know how long it takes the black holes to merge. So it's, you know, a lot of parameter space is in play. If you play a similar game with this Blazar OJ287 that has been suggested to be a binary black hole, you got a little bit more optimistic number than our most pessimistic. And then here's our best guess, which happens to fall pretty close to this, quote, theoretical gravitational wave floor. This is what you get if you imagine that all black holes stall, but there's going to be other black holes that come in, and those three Badari interactions will lead to some mergers, and that's their predicted very lowest background. So you can see that our predictions, there's a wide range of possible things between the black and the orange. I think the orange is probably too high. On the other hand, we're only looking at luminous accreting things, so in a way that's going to be low. What's interesting is that, you know, Chiara Mingarelli, she's a PTA person, she's very optimistic that the detection will happen any day. Once the background is detected, we can turn this right around and start to learn things about the black hole population. And so we feel like developing this machinery, which is to empirically link properties of the quasar population to predictions for the gravitational wave background, will turn out to be very fruitful for our understanding of black hole populations once the background is detected. And so one of the things we're working on is trying to better understand what this number density of AGN pairs should be. And so Chris was at the telescope recently and has found one tantalizing source. If you squint, you can see that this is not a PSF here at the center. And so we'll be just trying to perfect that number of pairs. It seems like almost everything at this highest luminosity is indeed in some sort of merger, see prior part of my talk. And so we'll just see what fraction of these do end up to be pairs of black holes at this moment. And that is, I'm going to skip that. That is everything I wanted to say about empirical AGN-based constraints on the gravitational wave background for now. It's been quite far from what we usually do, but fun to think about using these AGN surveys to put empirical constraints on the background. All right. So for the last bit of my talk, I want to come back to this question of the role of accreting black holes and mergers in shaping massive galaxies. And specifically, this question of how do we make big ellipticals? How do we remove their gas? How do we make them red? And I've been working with Rachel Bazanson and Mariska Creek to try and find a sweet spot of galaxies where their most important star formation episode has just shut off. So we're looking for these mythical post-starburst galaxies. But we want to find them at a relatively low redshift so that we can follow them up in some detail. So these are massive galaxies above 10 to the 11. Their spectra look like A stars because they just had a major star formation episode, but it has been shut off. And we are finding them in SDSS with spectroscopy. And so this is, Rachel and Mariska are better at branding than I am. This is the SQUIGGLE survey, studying quenching in intermediate redshift galaxies, gas, angular momentum, and evolution. Don't think about it too hard. And it's really a fun team of people. I've been having a great time, but I'll just highlight Ren Suez, who's a graduate student at Berkeley, and she's been doing a lot of the sample selection. And Dave Seaton, you'll see his name come up a lot. He's a graduate student with Rachel who's been doing a lot of the optical spectroscopy. And so this is the entire sample. There are about 1,000 spectroscopically selected post-starbursts in this redshift 0.7 range. We've been extremely successful getting ALMA time, and so we have things to say not only about their star formation histories, but also about their current gas fractions. So what Ren does to select these post-starbursts is she basically has these synthetic filters that Mariska developed that are very sensitive to a very prominent Balmer break. So we're not worrying about the line emission. You can have line emission and still be in this post-starburst sample. The point is that you're a honking A star, and you're very massive, above 10 to the 11. So that's the sample selection. One of the fun things we've been able to do is cross-match our 1,000 post-starbursts with the HyperSupremeCam data. And here are the residuals when you fit a single Sursic model. And what you can see is there's lots of exciting morphological disturbance stuff going on. So many, there's like 35 that have HSC data, and many of them show signs of tidal interaction. This is not a quantitative statement yet, but it is striking when you look at it. We also have Gemini data for something like 15 objects. So we've been looking at the kinematics. Kiana Hunt, who's now a graduate student at Michigan, looked at our first brightest object. It showed this really ordered rotation. Of course, none of the other objects show that at all. So they seem to be random. They seem to be dispersion dominated in general. And interestingly, they seem to show no age gradients. So David is just finishing a paper on this and asking, given our PSF, how strong are our constraints on the actual age gradients in this sample? But at least at face value, it seems like they are post-starburst across the whole thing. It's not a burst in the very center. Ren has been looking at the star formation histories, and it really looks like some large fraction of the total stellar mass was built up in the last starburst. But what's really exciting is that although there is basically no star formation going on in these objects, at least as probed by the oxygen 2 line, half of the ones we've looked at with ALMA have very large gas masses. So 10% of their baryonic mass seems to be in molecular gas. If you let us do whatever XCO conversion we did here. And then the other half are undetected. Interestingly, if you order them by the strength of their 4,000 angstrom break, so these are younger and these are older, we're only detecting molecular gas in the youngest of these post-starbursts. And this is work that Rachel is working on publishing. So I have to come back to the high energy angle now. I have been looking at the AGN objects in this sample. One of them we happen to look at with ALMA, and it's got molecular gas freaking everywhere, out to 15, 20 kiloparsecs. We're agonizing now about whether this is tidal or whether this is blown out by an AGN. The O3 is very broad. It's 1,000 kilometers per second, but it's pretty much concentrated towards the center. And our Gemini data don't go out this far, so we don't know if there's warm gas coincident with the molecular gas or not. But I wanted to ask a simpler question, so I just wanted to replicate Rachel's time since burst plot, except looking at the AGN fraction. So if I look at the AGN fraction as probed by the O3 to H beta ratio, I see that it's a few percent of the galaxies that show high O3 to H beta. These are 10 to the 11 solar mass galaxies, so I don't know what this would be if it was not AGN activity. But if I separate them into those that are youngest and those that are oldest, I find a dramatic enhancement of AGN activity in the youngest of our post-starbursts in exactly the same region where there still seems to be some residual molecular gas. And here's the stacked AGN spectrum, and we do see some neon 5 there, so I'm fairly confident that what I'm picking out are active galaxies. So there's this tantalizing hint that maybe AGN activity could be linked to the cessation of star formation in these massive post-starburst galaxies, and it's maybe just finishing clearing out the gas as we look upon them. No one really ever wants to ascribe causality too strongly in AGN land, but it is kind of fun to see this trend. So that's the end of the last part of my talk. These post-starburst galaxies at redshift 0.7 are ending their last major star formation episode. They've built up at least half their mass in this last burst. The youngest ones that we've looked at with ALMA still have high gas fractions, no ongoing star formation, and they also show this tantalizing excess of AGN activity. And I will stop there and take questions.
Thank you, Jenny. So questions?
So back to the AGN merger association.
Yeah.
As they merge, if they do get to merge, wouldn't they most naturally expel their gas and therefore cease to be AGN?
You mean, is the reason we never see quasar activity in type binaries because there's no gas around?
Yes. I would think it would be very hard to hang on to disks around each of the two individual ones as they get close to that final parsec.
I mean,
Has that been simulated? No.
the guy sitting behind you has thought quite a bit about this. There's a whole group in New York doing this, but they're not the only group. So I think you have to postulate an M dot, but you certainly can hold on to some either circumbinary disk or maybe there are then are mini disks. But of course, I mean, those disks are, are they eccentric? What's doing the fueling? I think it's very hard to know if there will be an electromagnetic counterpart. And that, I mean, when I was looking for shifts, of course, we had a large enough sample that if you wanted to postulate that all AGN activity was linked to a merger, then we really expected we should have seen a couple shifts. Okay, it was a marginally interesting detection, but of course, I mean, non-detection. But of course, there's always the issue of maybe they don't radiate at all when they're at this tight stage. I don't know what you do about that. Yeah.
When we think about the statistics of when you look first for mergers and then for AGN, is there anything one can learn from asking whether you see a single AGN as opposed to some binary wider than a certain resolution separation? In the sense that, like...
In terms of the gravitational wave background?
No, does that tell you that they merged at a certain point? Like, if you don't see binaries among your merging galaxies sample, binary AGN.
No,
does
because...
that ever tell you anything about whether they're merged?
I don't think so, because I think it's true, even for the most optimistic merger timescales, that the galaxy is relaxed before the black holes merge by, a giga or two.
I see. So those are never, like,
No.
contemporaneous.
And of course, you can find evidence for past mergers. You can find evidence for past mergers in every elliptical galaxy if you look hard enough.
Yeah.
So I don't think that helps you too much. Maybe the detailed star formation history, but yeah.
Yeah, that makes sense.
Yeah. And then we don't have the resolution. I mean, if you see one and you don't see two, that doesn't mean that there aren't two.
Right.
Which is why there could be
Right.
parsec scale binaries in the centers of all galaxies and we wouldn't know. Sadly, embarrassingly.
Thanks.
Rita, you
Oh.
have a question?
Yeah, the connection to the post-starburst galaxies is really interesting from the TDE angle. You may or may not have heard that one of the more interesting developments of the last few years is that they just have a really high transcription rate. So maybe it's not high enough to actually stimulate.
I think
emission, but the
yeah.
same processes could be, driving different sorts of material to the center.
Well, that's interesting. Yeah.
Yeah, that's all I have to say. For
Yeah, right. Yeah, so the fact, I guess I would say that the fact that, no, I have nothing interesting to say. I have to chew on that, I guess. You're suggesting maybe some large fraction of the fuel for the AGN could be TDEs.
Not necessarily, but in order to, it's not entirely clear why post-starburst galaxies have such an elevated TDE rate, but I mean, you could have, for example, a lot of gas that's driving nuclear starburst or something like that, as one idea for how you might be funneling a bunch of stars towards the black hole. It's correlation, it's not necessarily causation.
That's right. That's why I didn't want to say causation too strongly, but it is kind of fun that we see that relationship.
Kathy?
Yeah, I wanted to go back to the gravitational waves.
Sure.
What would a non-detection tell you with the instrumental limits that you can expect?
You mean at what point? Well, okay, so if you get past here, then we have some real problems. We're far from that. Is that what you mean? Yeah, then, I mean...
No, and also what, given the radio telescopes, etc., what type of limits can you put there on that?
Well, so this was our range, just based on the existence of these duals. This is OJ287. I don't know that there are other radio observations that are super useful. There are a lot of non-detection. So Sarah Burke-Spillauer didn't detect any binaries in some large number of radio calibrators, basically, that she looked through that were very high resolution VLBA calibrators. But again, you're relying on there being an AGN. So we can kind of get away with this because we're sort of implicitly assuming that the AGN tracks the merger rate. And if you're luminous enough, you have to be a big black hole. So we get the black hole mass distribution from the luminosity, and we get the merger rate by this assumption that merger and black hole go together. And that gives us a range. I don't know if there are other AGN observations that it would be interesting, but I haven't maybe thought hard enough about the radio. Did someone?
Yeah,
I'm sorry, Igor.
sorry.
Yeah, yes, go ahead.
When you think about the evolution of the binary between redshift 1 to redshift 0, do you assume that it creates in that period, or do you assume it merges at the mass it has according to redshift?
We assume it keeps that mass the whole time, and we assume that the time scale that we assume doesn't go, we don't let it go faster because of having accretion disks. We just basically assume that it is able to get over the final parsec problem with stellar scattering. And so that time scale is, of course, very uncertain, but we just basically make them merge. So at a certain point, gravitational radiation takes over. Yeah.
In the very beginning of the talk, you mentioned that apparently there were no direct observational evidence for merging of supermassive black holes.
Yes, subparsec
But
binaries.
wouldn't you consider what we see in Andromeda, where there is an off-centered black hole in the very central part, which is off-centered with respect to the photometric or mass center of the bulge, an evidence for the past merger that happened relatively recently? In Andromeda, in M31, the 10 to the 8 solar mass black hole is not in the center of the galaxy. It's offset by a couple of arc seconds. And there's a velocity, like it's a very interesting configuration. It's what was
I am
discovered
ignorant
by-
of this, so I know that there's an eccentric disk. Is that what you're
Yeah,
talking about?
eccentric disk, and there's a black hole in one of the clusters, which is on the orbit around the center of gravity.
There's a second black hole?
No. There's only one, but it's on the orbit. It's not in the center, in the photometric center of the bulge of Andromeda. The main black hole, the only one that we know of, it's not in the photometric center.
Okay.
But isn't it at the focus of the eccentric disk?
Yes,
Yeah.
there's an eccentric disk, but isn't it an evidence for the past merger that happened pretty recently?
I think
Because
it's
there
just
was
an
a kick,
eccentric
there was a
disk.
kick.
It doesn't have to be that way for sure.
Yeah.
You can form an elliptical. I mean, like Phil Hopkins has a paper on this where he shows that you can form during a quasar accretion, you can form an eccentric disk.
So you mean there are other mechanisms? It doesn't have to be a merger to push it out.
Yeah.
Any other questions? Okay, if it's not the case, then let's thank Johnny and thank you all for the excellent discussion.
Strange.
Thank you.
Very popular.
Yeah. Maybe I had time. I could have talked about the intermediate mass black holes too.
Can I ask you a follow-up question?
Yes, of course.
Oh, by the way, I'm Magda.
Nice to meet you.
I'm an art student.
Okay.
So you said you're going from the stellar scattering phase straight into the gravitational wave emitting regime?
Yeah.
Is that because you're not trusting the torques, or?
I mean, that would make it a little bit faster, right? So we just did, I mean,
it might not make it faster, right? Because recently people are seeing positive torques.
oh geez.
I know.
Yeah, so we did nothing sophisticated. We did like an analytic thing to get them to merge, basically. And so I do think, from the empirical side, the only things we can really improve are sort of the number densities. That's what we're really getting from the observations. Oh, yeah. Thank you. I didn't mean to be blasting the world.